Very good morning, everyone. Let's begin the class and let me just check whether the sharing is enabled. So yeah, my sharing is activated. So let me just start with the blank PPT so that I can just write there. Yeah, okay. So screen sharing is activated. I hope you are able to see the screen. Yeah, so very good morning once again. And well, now we are going to progress towards better concepts of programming using pointers, etc. Earlier, I also already said that slowly our programming will become more interesting and will require uh, more practice also. So now pointers based programming will start. So till now, we have effectively tried to go from the sorting and a traditional sorting. Then we were able to go towards the linear sorting, and then we were able to improve the time. The focus of the algorithms is always that we should be able to improve the time complexity, maybe with certain constraints. Similarly, let's go with the searching also. Now, just imagine in searching, what is the time complexity? Over an array, whenever you did a searching, if you did linear search, you know what was the linear search time? Linear search was order of n. Then you have also done binary search. For binary search, what was the time? Of course, order of log n, searching time. But if I wanted binary search to be to be implemented and used, the array must be sorted at all times. Now, maybe sorting initially can be done over the data, maybe whatever time it takes, one time, but not a big issue. But if insertions were frequent, insertion in case of an array, that is going to be a costly affair. Insertion in an array is going to take order of n time. For example, if I have values 5, 10, 15, 20, 30, 40, and let's say insert 2. If it was an array, there is no other choice, but you have to shift all values towards right, create a place for 2, and then 2 comes here. That indirectly actually will mean 40 will come here, 30 will come here, 20 will come here, 15 will come here, 10 will come here, 5 will come here, and then I will have the same thing done like this. So insertion is going to be costly. If insertions are frequent, then my binary search over an array doesn't become good choice because insertions will take more time. So I have to think of solution. So now another solution comes into picture and we call that as a binary search tree. So for such situations where insertion will be also frequent along with the searching. So if insertions are frequent along with the searching, then searching although becomes log n, but insertion becomes more time consuming. So binary search tree can be a good choice. Of course, it requires the concept of a binary tree, and we can definitely use this binary search tree. So it also has certain terms and conditions we will see, but binary search tree, as the word suggests, it's a binary tree specially useful for searching. So I have binary tree as searching option available. Now, how that happens? So effectively, it says that for every node, for all nodes, I'll say for each node, the value of the node has to be greater than its, or I'll say greater than its left child and less than its right child. So greater than its left child and less than right child. Effectively means root is in between, or root or current node is in between. So left child is less than the root node's value and in turn, this is right child's key is again in the same. Right child key is again in the similar way. For example, if I say, let's say I have a 12 here. So I have 5 here. Maybe I have here 15. So I can say 12 satisfies this property. But not only 12, every node has to satisfy. So for 5 also, the values has to be something like this. For 10 also, the values have to be satisfied. So for 2 also, like this value has to be 6, but this value can be 1. Now 6 will be incorrect actually, because 2 satisfies this value 6, but actually this 5 has to have 6 on the right side of a 5. So I will say the whole left subtree, the value of the left, this I will say to be precise, it's greater than full left subtree, and this value is less than right subtree. So I can easily see now that the values 6 will be incorrect here, because 6 is on the left of a 5, so it cannot be on the left of 5. Had this value been, let's say, 4, then it satisfies this. So binary search tree, if we have things like this, let's say I have here 20. So 20 can have any value on the left will be, which value has to be less on the 15's right. So it has to be always guaranteedly, value has to be greater than 15, less than 20. For example, 70. All values on the 12, they have to be greater than, on the rights of the 12 have to be greater than 12. And all values on the right of a 15 have to be greater than 15, and like that. So one good thing about this is all key values are unique. We assume that all key values are unique. And for a primary key, effectively in real applications, the primary key is always unique. So my BST will be always maintained based on some primary key, and primary key is by default unique. So there will be no duplicacy available, and but automatically that all during effective searching, etc., will be ensured. So by doing this, we can easily see that we have the searching option becoming something similar to binary search, but we need not have the insertion to be always order of log and time. My insertion also can be in order of log and time instead of order of n time. So insertion will be in order of log n if a tree is not imbalanced. So there is a danger that a tree can be imbalanced also. When and how, we will see after a few minutes. But if it is not, my insertion and searching both will be order of log n time. So that is what we will be able to achieve through this process. And going further, so binary search tree can be a good data structure for situations where searching and insertions are frequent. And if we can ensure not imbalanced, then in log n, most of the operations will be possible. So I will be able to do operations, most of them in order of log n time. What are the operations? For example, first operation is search. Second operation is find minimum value from the tree. So search for a value, search for a key, I will say to be precise. And then find minimum from of the binary search tree. Third operation can be successor to be found, successor of a given key, successor of a given node, I will say. Given a particular node, successor to be found. And then, of course, other operations being insert and delete. So we have these operations to be implemented. Let's go one by one and understand what we are doing. First, search. Well, as the word suggests, mostly searching will be definitely needed. Search for a key. Why for a key? Like if I have a record of students, so student record has many fields, not only the roll number. So a record of students, and let's say key is roll number. So once key is roll number I know, but I'm not just interested to know the roll number. I'm willing to know many other details of that student. And if I say that based on the key, I will be able to search for that roll number into the binary search tree. Once I reach to that particular node, I will be able to refer to that particular other fields of this. For example, if I said in this tree, I want to go to roll number, say 10. I'm interested to go to roll number 10. So 10 will mean I reach to this node, but along with this 10, there are many other values also which are stored at this place. So all those values are also stored here, and all those values will be available. 10 I knew, so my purpose is not obviously to search for 10 value, but if 10 exists or not, that is one requirement. If 10 exists, other fields to be used and processed for that. Obviously, so I will have to write some function for this searching. What should be the parameter? Obviously, node star BST. So what is my node star? Node structure I can easily define. So node structure will definitely mean the value or the data as a key, whichever is there. Other fields also can be there. Say if I want to store roll number, along with roll number, the name, mobile number, etc., etc. Plus, definitely, I will have node star left, node star right. Just like in case of a binary tree, we have been doing that. So simply a binary tree. Because it's a binary search tree, so it is effectively a binary tree with the special properties for the values to be satisfying the condition of left subtree being lesser than the root and right subtree being greater than the root. What we should return? Obviously, I should return the node so that I can easily get the other details from that node. Now, of course, how to make the logic? There can be many situations. If BST equal to null, obviously I know what to do. I can easily have the return statement and something to be returned. If the value, maybe let's say I want to search, so that parameter also needs to be passed. So the value to be searched, let's say int k, or based on the key value I will be searching. So I will say if a k equal to BST arrow data or BST arrow key, whatever field name you have used. Let's say you said BST arrow key. So if k is equal to that, obviously what I have to do, again, I can do the corresponding return type. And the purpose of using return is simply that I need not write here else. So even if I don't write else here, still it is fine. Even if I write here else, still it is fine. It may not differ at all. Else. Now, it can be recursive also, like in binary search you have done. It can be non-recursive also. But the logic is simple. Effectively, if k is less than this BST arrow key, where you have to search? You have to search actually nothing but in the left subtree. It may exist, it may not exist, but if at all it exists, you have to go into the left subtree. Similarly, else you have to search in the right subtree. It might not exist also, accordingly, you should get none. Now, as the word search comes again in the same search module being implemented, recursion can be easily visible and you can easily write a recursive module for this. But non-recursive is also equally easy. You can practice both and do that. For example, just to have a look, let's say I wanted to search for roll number 10. So obviously I will start from here. 12, 10 is less than 12. So guaranteedly, if 10 exists, we have to go to the left child. I come to the left child, 5. 5 is guaranteedly lesser than 10. So it means 10 has to be on the right side if at all it exists. From the 5, I go to the right child, 10. Yeah, 10 I got and done. Let's say I wanted to search for roll number 7. Say 12, you came, 7 has to be left side. You came here, 5, 7 has to be on the right side. Right side, you went to 10. 10 means if 7 at all exists, it has to be on the left side. Left side is empty. Left is null. That means 7 doesn't exist. So left is null, 7 doesn't exist. Maybe I can return a null pointer and accordingly I can say 7 doesn't exist. So null return will mean that it doesn't exist. So search can be done like this. Going to the next operation, find minimum. So think of now, where will be the minimum value of the binary tree? So of course, node star BST to be passed. What it should return, minimum value is to be returned. So I can either return the key value or I can have node itself to be returned. So I can have a node star to be returned because it may have all other values available. So as per requirement, I can choose that. Simple. Just go to the tree. Where is the minimum value? This is the minimum value. So minimum is easy to think because every node has a property that left 12's smaller value is available on its left. 5's smaller value is on the left. 2's smaller value is on the left and so on. So effectively, I have to do nothing but reach towards the leftmost child. And that becomes automatically minimum. So my minimum easy, I have to go to leftmost child. That's it. Leftmost child. That's it. So that will be automatically the minimum. So not a big deal. And if it is already the minimum, if it doesn't have leftmost child, so the root itself will be the minimum. So accordingly, I can get that. Then coming to the next operation, successor. So again, you have to decide what should be the return type. So I will say what should be the return type. Maybe node star you can think of, successor function to be returned. What you need to pass. Maybe you have to see what you need. So I say successor of a given node. Say node is told to me, say given node X. How will I reach to X? Maybe by searching for a particular key value, I will reach to X. So once I have reached to X, I want to find out successor of given node X. What does that mean? Successor means next value which will come as its corresponding in order traversals next value. Well, if I see carefully what is going to be the in order traversals next value for any value. Let's say I want to talk of some value 15. So 15's next value is probably 20. Maybe I can simply say go to the right child downwards and then probably that is it. Yes, might look simple, but just see what is the 12's successor. So 12's successor is 15. Yeah, I can easily see. So 12 successor appears to be this. But maybe I can say just to find out successor of 1. Successor of 1 is 2. So there are not very clarity what will be the successor. So let's take some sample case from where the logic can be made. So I have 12, 5, 2. Let's assume this side I have 15. So from 5 I have 7. From 7 I have 9. And from 9 I have, let's say, 10. And from 15, sorry, let's say I have 20 here. From 20 I have, say, 19. From 19 I have, let's say, 70. Now see more carefully that what is successor of 15. successor of a 15, how will you find out? Sorry. So successor of 15 you can see is a 17. And now that becomes a logic that effectively not simply the right child, right side of course a successor will exist, but on the right side I have to go to the minimum value on the right side. So effectively I can say minimum value of the right child of the right subtree will be the successor. That once I say, that becomes a good way to find minimum value of the right subtree. So if I'm talking of 15, the right subtree is starting with 20, minimum of that is 17. If I am talking of, let's say, 7, 7's right subtree is 9. 9's tree's minimum value on this side will be obviously 9. I can easily see that logic and like. So I say effectively successor will mean two situations. First situation, if right child exists. If right child exists, then effectively minimum value of right subtree will be the successor. And how to find minimum? I have already defined just now the find minimum of a particular tree. So considering this subtree's current node as root, you can call that find minimum, and then you will be able to reach that. Then second option, if right child doesn't exist. For example, going back and I say, I want to find out successor of 10. So successor of 10. Now 10's right child doesn't exist. Successor of 10. Now 10's successor, I can easily see if I do the in order traversal, 10's successor will come out to be 12. If I say 7's successor, it was 9. 5's successor, it is 7. But if a 7 had, let's say, a left child, then 5's successor will be 6. What if 6 successor? 6's successor is a 7. 10's successor is a 12. So if right child doesn't exist, then I have to go towards the parents. But not simply going to one parent. Like for 6, going just to one parent I could get. For 10, I have to go to many parents and reach to the 12. Then what should be the logic? So now if I see carefully, see, each node has a property that right child, if at all, is greater. So if I am going towards a parent, and if I am the parent's right child, that means my parent is a smaller. So it cannot be the successor. So I have to climb up many a times. From 10, go to the parent. As I am the right child of 10, right child of 9, still successor not available. From 9, again go up. I am still the right child, again go up. I am still the right child, again go up. I am now the left child. So if I am the left, very good morning all of you. Let's resume where we were talking, and I hope my screen is shared. Let me just confirm. Yeah, that is correct. So just when the recording stopped, we were talking of the issues related to successor, and we have already seen some of the basic insertion process and some of the basic issues related to successor. So our last discussion was continuing with the successor to be found. So we just said that, yes, as soon as 5 has got the 12 as its parent and 5 is on the left side, so I am able to get my successor. On the other hand, just imagine I have to find out successor of a 20. I'll go up 15. 20 is the right child of 15. So 15, it cannot be the higher value than 20. So it is not a successor. 15 again climb up. 12 is again having the 15 as a right child. So again climb up. When I try to to go up, climb up, then I have now reaching to the null. So that means successor doesn't exist. So only for situation like this, successor won't exist. Otherwise, successor will exist either as we said that on the right side child, or we will have on the left side, we will have go towards a parent and keep on going as long as I'm the right child and stop immediately when the node is left. And null can also come. So null if I reach to the right. Without satisfying, without being the left child. So if I reach to this without being left child, that will mean unsuccessful case. And then I can easily say that I should return null. So this becomes successor. Then another important issue before we go to insertion is that we can do the traversal. And for BST, of course, any kind of a traversal we can think of over a binary tree. So we know already in order, pre-order, post-order. All traversals can be easily implemented over all these three situations. All these three traversals can be implemented. Some results will come. But in-order traversal is going to be one of the most useful for us because it will give us nothing but the left data, right being the thumb rule. Left value is guaranteedly the smaller values than root. Then the data will come. And then right value, which is going to be the bigger value than the root. So I always know in the case of a BST, we will again recall that for any node, whole left subtree is guaranteedly less than the tree root value. This value is guaranteedly less. Similarly, whole subtree on the right side is going to be greater than this data. So knowing this, I can easily see that once I do in-order traversal, I will get the sorted list of all values in ascending order, of course. So in-order traversal will be definitely very useful to find a sorted array or sorted list. Of course, another thing to be noted is that in order, or for that matter, any order traversal, the time complexity we can always calculate. Of course, they all are recursive in implementation. So one way could be that you can solve using recursion tree, recurrence tree to be defined, and recursive relation or recurrence relation to be solved. That can be one way of doing. But other way can be there that I can directly tell that in all these traversals, it is almost sure and convincing logic that each node will be traversed. That is for sure. Traversal means each node must be traversed. And secondly, once traversed, there will be nothing else to be done from that node. Internally, while recursion uses stack, pushes, pops, that's not a big deal. But I say each node must be traversed once, and to be precise, exactly once. If so, then come what may, whatever recurrence relation I write, my time complexity is guaranteedly going to be always a theta of n. And that is but obvious also. Anytime I want to traverse the whole list of n elements, all elements need to be traversed. So n time will be always taken. So theta n will be the time complexity. In fact, if you see successor to be found, successor means nothing but effectively value next in the in order of that particular. So successor means nothing but in the in-order traversal, the value which comes next in the in-order traversal. But of course, I should not find the successor using in-order traversal and then finding that, because that will mean the total time taken will be theta of n, because in-order traversal will be done. On the other hand, the successor can be definitely found in order of log n time if the tree is balanced. Why? You can easily see for successor, either you will go towards the downside. If you are going to the downside in one direction only, so we will go to the right child and then keep on going to the left child, left child, left child. So that will mean worst case, we will go height times. Height means effectively log n. So I can easily see in this case, successor will be this. Else means I don't go downside, then I will go again upside, going upside towards the parents. Again, maximum possibility to go upside up to root will mean that again it is going to be height times. And height times mean obviously again order of log n. So either because of a second case I will get log n, or because of a first case order of log n. But total time complexity for successor, one of these will be only applicable. So we will be able to solve it in log n time. So knowing this, now we go to the two most useful operations, which we call as insert and delete. So we will go for insertion first, and then we will go for a delete in the next class. Insertion. Well, let's say insertion to be done, if I have value say 12, I have here 5, let's take the same previous data. So 15, 20. 15, 20, and so on. Now just see, let's say if I want to insert 13, so I should not try to put it here, or maybe if I say I try to put 18, I might not be doing a good by putting 18 here. Why? Could be I have a 17 here. If 17 is here, 18 put here, it will make 18's right side as a 17. So many problems. Secondly, having this will disturb so many other links and all those checks to be done. So insertion is implemented in a simple way by saying that inserted node will be guaranteedly leaf. First thing is will become a leaf, and it will be inserted, or it will be connected at the place, at the deserving place where vacant pointer is available, and deserving pointer which will be vacant means either left pointer or right pointer will be available as a vacant. Only at that place I will insert. And the good part is this will be always possible. How? Simple. Just recall search. Let's say I have here 25. I wanted to insert 18. Say search for 18. Ultimately, for searching for 18, if 18 doesn't exist, you will reach to null pointer somewhere. So if you apply the search logic, you will reach to null pointer where you will claim that 18 doesn't exist. Say if I am trying to insert 18, for that the logic I start is search logic for 18 is good enough to tell me which place it deserves. Ultimately, null pointer will come somewhere, and then I will say no, and probably that is the right place. That is exactly the place to insert 18. Exactly the place for node 18. What does that mean? Let's have a look. For example, let's take quickly the one binary search tree, 12, 5, 15, say 13, say 14, say 18, or I'll say I have here 20, I have here 25, maybe I have here 70. What I will do? Start from here, 12 versus 18. 18 has to be on the right side. I will say go towards right, the way we do in the searching. Go to 15. 18 has to be on the right side. Go towards right. Right child exists means I can't stop. I have to further go. 20. 18 has to be the left side. I'll go towards left. Left still exists, so 18 can't come here. Compare with the 17. 18 has to be its right side. Right side link is empty. So this will be the place where 18 will come. So what ultimately I have to do is make 18's left child as null. Don't forget to make these null, otherwise later you will face a problem. And also don't forget to update your parent link, because in successor also we saw that maintaining parent link will be desirable. So during insertion, make sure that you update the parent pointer also every time. That effectively means everywhere the parent link is also properly maintained. So internally, all these have already got the parent link also working correctly for all these nodes till now. And this is a new node added. Say I wanted to insert, let's say 3. So obviously compare with 12. Left side still exists. 5. 3 has to be left side. Left side is free. I can have a 3. Not an issue. Of course, make this link also. This side null and other side also null. So maybe insert, I say insert some value, maybe something like could be, I'll say, let's say insert 4. Compare with 12, go to the left, left exists. 5, 4 is to be left, left still exists. 3 is the right side is available. 4 will come here. And accordingly, all that will be done. So this way you can easily do. The only thing to be taken care that either if you just use, I'll say, if you just use the insertion logic, ultimately, if you use the search logic will bring you to the null place. And if you have come to the null place, how will you come to know from which node you came back? Which node you came here? So you need to maintain a previous pointer so that you know from which node you came to this node. What does that mean? Effectively means nothing but, so you will have some kind of a while loop, or you will do some recursive. Say you have some PTR initially equal to root or BST. Say you have BST root, and then you will start doing something. And ultimately, either you will say that based on some if, you will say PTR equal to PTR arrow left, or PTR arrow right. Either you will go to the left side or you will go to the right side. But when you are going to stop, ultimately, when you come here, while you might have something like while PTR not equal to null, and you might have some condition, but coming here, because you are searching for a non-existence value, ultimately or guaranteedly you will be reaching to a position where you reach to a null point. So if you reach here now, you have the new node But whom to connect a new node? New node to be connected to whom? I have no information available. So what I will do is, sorry, I'll maintain a previous node saying PTR. Sorry. And now I can easily say that previous nodes left or right will become equal to new nodes. But which side? Yes, maybe you can use either a flag here to know which side ultimately you moved. So maybe you can say flag equal to 1, flag equal to 2, and now using that flag you can do. So maybe either use a flag, but without flag also you can do this. How? You can directly compare previous node's data versus new node data. Like if a previous node is less than new node data, means root is, or my parent is less than new node. So in that case, I will say previous node arrow left to be equal to new node. And otherwise, it will be on the right side. So I can say either I will use flag or I will compare these values. So you can use any logic, doesn't matter. Both are equally good and simple. So you can use any logic for these situations. So I hope by this things become easy and you can do the insertion implementation without much difficulty. I think let me wind up the class here, and next class I'll show you some of the sample code, partial code for these operations, and then discuss in more detail the deletion example. Bye-bye. Best of luck. All the best. Try to implement all these. And if you find difficulty, my next partial code will help you in finding the solutions. All the best to all of you. Let me stop the recording.